This video covers section 11.2, exponential functions. Objective 5, use exponential models that describe our world. The exponential functions are used in many different disciplines, such as biology for half-life, chemistry and carbon dating, and economics, time value of money. The practice problem that I want to work with is the half-life problem. The half-life of a substance is the time it takes for half of the substance to decay to some other substance. So that is, if I take some kind of substance, the half-life is the time it takes for half of that substance to remain. Another time of half-life that goes by, and now you have a half of what you had before it, or now 1/4. 1/2 goes away, 1/2 of a half is a quarter. Caffeine has a half-life in our system. We metabolize the caffeine when it's ingested, and it says after 5.7 hours, half of the caffeine is decayed or metabolized or gone away from our system. So suppose that you consume 80 milligrams of caffeine before class starts. The amount, which we call A, in milligrams of caffeine in your body after T hours is given by A equals 80 times 1/2 raised to T over 5.7. One thing to check is how this T over 5.7 comes about. So what we're saying is if T equals 5.7 hours have passed, the amount of caffeine present after you ingested 80 milligrams should be 40. So plugging that in there to see that happen, 1/2 to the 5.7, because T is 5.7, divided by 5.7 says 1/2 to the first power, or just 40. So these half-life formulas always take on the form of 1/2 to the T over whatever the half-life is. So how much caffeine will be present in your system when class ends? Well, class typically isn't 5.7 hours. So we can expect to have more than half still in our system. But let's suppose that class time is 2.5 hours. Let's suppose your class time is 2.5 hours. Remember, it takes 5.7 hours to cut the 80 down to 40. So we've got less time than that. So we should have a lot more than 40 left over. So we plug that into the formula, which says that the amount of caffeine present after 2.5 hours is going to be 80 times 1/2 to the 2.5 divided by 5.7. So now you're going to need, for these, to calculate these, you'll need a scientific calculator. I'm going to show this to you on a calculator that can be used online called Desmos. So we have 80 times 1/2, or 1 divided by 2, raised to the 2.5 over 5.7. So the result on that is 59.028165. We just need to say that's around 59 milligrams. So we would estimate that and say there's about 59 milligrams of caffeine present when class ends. So you can see it takes quite a bit of time to get rid of the substantial amounts of caffeine present in our system after we ingest these. Another example we look at for applications of exponential functions is money deposited into a bank. The bank pays us interest on the money in the account. When we let them have our money in there for a while, they pay us interest on our money so that they can invest it and make money for themselves. When solving interest problems, we use the term payment period to indicate how often the bank pays interest. If a bank pays you interest annually, it will just be one time a year. If they pay you semi-annually, it'll be twice per year. Quarterly is 4 times a year. Monthly is 12 times for the 12 months. And daily is 360. I usually like to use 365 times per year. When the interest that you earn is added back to the balance in the account, the new interest is based on the increased amount, and we say that the interest has been compounded. So here's the compound interest formula. The amount of money A after T years resulting from a principal P, which is the amount of money invested, at an annual interest rate R compounded the N times per year is given by A equals P times 1 plus R over N raised to the NT. So an annually N is 1, semi-annually is 2, quarterly is 4, monthly is 12, daily is 360 or 365. So suppose that you deposit $10,000 into a Roth IRA. The principal is $10,000. We want to determine the future value A of the deposit if it earns an interest rate of 0.05. We're going to compound everything monthly so that N is equal to 12. So if we do this just for 1 year, it's going to be N is equal to 1, which gives us the amount is P times 1 plus R over N raised to the N times T. 10,000 is the principal. The rate is 0.05, and the N is monthly or 12. And we want to do this for 1 year, or T equals 1. So we'll need a calculator to do this. And so we'll take 10,000 times 1 plus 0.05 divided by 12 raised to the 12 times 1. And we get 10,511. And 62 cents. So let's just go ahead and estimate this as 10,511 and 62 cents. And for the next one, we're going to do this for 15 years. So t equals 15 years. So we have 10,000 times 1 plus 0.05 over 12. 12 times 15 this time. So going back to the original calculation, we're changing 1 to 15. Now we're looking at 21,000 $137.04. So we've more than doubled our money after 15 years. And when it starts to get good is when you do these things for 30 years. So 30 years now, we change 15 to 30. The 15 years gave us 21,137.04. And the 30 years, we change 15 to 30, 10,000 times 1 plus 0.05 over 12 raised to the 12 times 30. Changing the 15 to 30 gives us $44,677. So we started with 10,000 and now we have $44,677.44. That does sound like a good amount of money, but imagine that it was $100,000 that you got to invest. Then you'd have $446,000 as a result of that. So that's how the compound interest formula works. And this concludes the video for section 11.2, exponential functions. Objective 5, use exponential models that describe our world.